All right, guys, today we're going to start talking about the unit circle. I'm going to walk you through filling this out once. We'll do this together, but in the future, this is something you're going to need to be able to do on your own. A lot of the questions at the end of the year on that AP test involve trigonometry, and some of those you're not going to have a calculator. And knowing some information about the unit circle is going to make those trigonometry questions a lot easier for you. Because instead of having to memorize it, it's just something that you can build and refer to when you need to. So what we're talking about is, first of all, this is a unit circle. So that means my radius is just 1. So from the center to the edge, anywhere around the circle, I'm just dealing with a radius of 1. And what we're going to do is we're going to start by measuring something called radians. Now, normally when we're talking about a circle, if I were to go all the way around this circle, you would tell me that that distance is 360 degrees. But in calculus, we don't use degrees. In fact, on the AP test, you won't see degrees at all. They use something called radians. So when they measure the distance around this circle, they don't want it measured in 360 degrees. They want it measured in radians. And in radians, that distance is going to be 2 pi. Because if I take 2 pi, and times that by my radius, that is going to give me the distance around the circle. Now in this circle, our radius is just 1. So my distance all the way around the circle in radians is just 2 pi, all right? So expanding that to the rest of the circle, if all the way around the circle is measured 2 pi radians, halfway around the circle is half that distance, which is just pi radians. I'm only going halfway around the circle. Going a quarter of the way around the circle is a quarter of this amount, but it's also half of this amount, right? So that's going to be pi halves. And if I go 3/4 of the way around the circle, I'm in between 1 pi and 2 pi. And so we're going to measure that as 3 pi halves, in between 1 pi and 2 pi. So those 4 are pretty quick, pretty easy to come up with. This 2 pi, if I were to start here, this is also 0 degrees. And because I haven't gone anywhere, it's 0 radians, which falls right in the same place as 360 and 2 pi, which will lead to some interesting things later on. But let's keep breaking up our circle. Let's start by, if I just take the top half. Now I've already broken it in half, and I've already broken it into my fourth. So let's take those fourths and let's break them again. So basically what I'm doing is I'm taking the top of my circle, just this half of it, and I'm going to break it into 4 even parts. So if all of the way around is 1 pi, and I break this into 4 equal parts, then that means the distance to this first quarter is a quarter of a pi, which is just pi fourths. So this first angle right here in radians is pi fourths. Now, if I go another fourth of a slice to here, I end up at pi halves, which makes sense because 2 pi fourths simplifies to pi over 2. So if I go another fourth, now I'm at 3 pi fourths. And if I go another fourth, I'm back to pi. All right. Now from there, I can keep going around the circle. If I go another fourth, I'm at 5 pi fourths. And another fourth would take me right here to 6 pi fourths. But as you can see, 6 pi fourths, we've already found that that reduces to 3 pi halves. So if I go another fourth, instead of 6 pi fourths, now I'm at 7 pi fourths. And then one more takes me to 8 pi fourths, which I already have as 2 pi. Okay? So that gives me a few more angles, but I've got all of these in between ones that we want to find as well. And let's break this up one more time. I'll try and do this just a little bit smaller. So instead of breaking this, I'm still going to break up the top half first. But instead of breaking the top half into 4 pieces that are equal, I'm going to break it into 6 equal pieces. So I'm going to take this pi distance and I'm going to break it up into 6 equal distances. So what that means is the first section right here, the first one I come to, is a 1/6 of the way around. So that is just pi 6th. My next 1/6 is right here, and that becomes my 2 pi 6th. My next 1/6 is this one up at the top, but we've already found 3 pi over 6 just simplifies to pi over 2. So if I keep going from 3 pi over 6 to here, I get 4 pi over 6, but let's not write that because that simplifies, right? 4 pi over 6 is going to simplify to 2/3 pi. So let's simplify that one. Let's make that 2 pi thirds, which this one also simplifies. We might as well do that now. We were going to do that later, but since we're talking about it, let's go ahead and simplify. 2 pi over 6 simplifies to pi over 3. The 2 over 6 reduces. So if this one was, we were at 3 pi 6s, this was 4 pi 6s, that makes this one 5 pi 6s. And then this one would be 6 pi over 6, which we already have as just pi. And I can continue my way around the circle. That would make this 7 pi over 6. That would make this one 8 pi over 6, which reduces to 4 pi thirds. And if I go from 8 6s, if I go another one to 9 6s, 9 pi 6, that simplifies to 3 over 2 pi. So let's go another one. This one would be 10 pi over 6, which reduces to 5 pi thirds. So we'll put 5 pi over 3. And then my next one is going to be 11 pi 6, which doesn't simplify. So we can leave that as 11. Well, I turned my 11 into my pi. I can make this one 11 pi over 6. And then, of course, if I go one more 6th, then I'm at 12 pi over 6, which is just 2 pi. Okay? So that right there, that's a big chunk of the unit circle. That's all of our angles. That's the first thing that we want to make sure that we know and are able to find. From there, we also want to be able to find our ordered pairs. We're not just interested in what the angles translate to in radians. We're also interested in, at this point, at pi over 6, what's my ordered pair? What's my x and my y? So the way that we're going to do that, we're actually going to start with, I'm not going to start with pi over 6. I'm going to start with pi over 4 again. So we're going to come right here to pi over 4. And what I want to do is I actually want to make a right triangle right here. Because if I take a minute and look at the angles, and I know I told you you're not supposed to do that anymore, but for just a minute, if I take this triangle that I drew and look at the angles, I'm halfway to 90 degrees, which means that this angle right here is 45 degrees. And since this was a 90-degree triangle, this is also 45 degrees. Now I know my hypotenuse is 1 because this is the unit circle and that's a radius. So I know that that is 1. What I'm looking for, here's my x value and here's my y value right here. Those are what I'm interested in. So if I look at the Pythagorean theorem, I know that x squared plus y squared is equal to 1 squared, which happens to just be 1. And if you remember a few things about secondary math 2, if both of these angles are 45 degrees, that means that these two angles, or these two sides, excuse me, are actually the same distance. So instead of calling one x and one y, they're the same distance. So let's just call that x squared plus another x squared. So when I simplify this, that becomes 2x squared equals 1. Now I'm looking for my x value. So I'm going to divide by 2 on both sides. So I'm going to end up with x squared equals 1/2. And I want to get rid of the squared, so I'm going to take the square root of both sides. So x is going to equal 1 over the square root of 2. And we don't like that square root on the bottom, at least not today. So remember in Math 3, you learned to get rid of a root on the bottom, you multiply by that root on the top and on the bottom. So my x becomes square root of 2 on top, and root 2 times root 2 is just 2 on the bottom. So that becomes my x value. So at this point, my x value is root 2 over 2. But if you remember, my y value is the same because it's a 45 triangle. So my y value is also positive root 2 over 2. Okay. Now, the nice thing about the unit circle is once you find one of these points, you can easily transfer that to the corresponding angles. So this angle was between 0 and 90, and it matches this angle right here, my 3π4, which is between 90 and 180. The only difference is I'm going in a different direction. Instead of going to the right root 2 over 2, I'm going to the left root 2 over 2. So I want to make sure that I use a negative root 2 over 2 as my x value, but I'm still going up. So my y value is still root 2 over 2. Now I want to do the same thing, but instead of between these two, let's look at my angle in between 180 and 270. So instead of going over to the right root 2 over 2, again, I'm going to the left root 2 over 2. So that distance is still the same because that triangle is the same. But this time I'm going down. So my y value is also negative root 2 over 2. And then if I transfer that to this last section, my corresponding angle is this one right here, my 7π4, excuse me. And this time I'm going to the right, so it's root 2 over 2, but I'm going down, so that's going to be a negative root 2 over 2. All right, now in the future, I'm not going to go through those as slowly. I'm going to let you do some of these next ones, but let's build those triangles first, because right now I got my 45 angles, but I'm missing all of these other ones, okay? I guess we could have started with, and maybe we should have done this to begin with, but at 0, if I'm just going straight out to the right, that x and y is a pretty easy one to fill in because I'm going to the right my entire radius, which is 1, and I'm not going up and down at all. So that's 0. But if I look at my angle up here, if I look at pi halves, I'm not going to the left or right at all, and I'm going up 1. And if I look at 180 degrees or pi, I'm going to the left 1, so that's negative 1, but I'm not going up or down. And down here at the bottom, at 3π halves, I'm not going left or right at all, but I'm going down 1. Okay, now for all these in-betweens. So those ones, again, relatively simple if you can remember the Pythagorean theorem. There's actually another way to find that distance with a 45 degree angle that requires you to remember some trigonometry. And I don't know if all of you have seen that yet, but maybe we'll cover that in class just so that you can see the other way to find that distance. But as long as you can remember the Pythagorean theorem, you should be okay. So now we are interested in these angles right here. And we're just going to start with this first quadrant again. So I'm going to start with this angle, and I want to find my x and y values. So again, I'm going to make a 90-degree triangle. And if you ignore what I said for just a minute, when I told you to forget angles, we're not going to do that for a couple more minutes, because this angle right now, if I'm a third of the way to 90, that means that this angle is 30 degrees. And since this is 90, that means that this angle up here is 60. So I have a 30, 60, 90-degree triangle, which is convenient because you learned about a special triangle like this one as far as how the lengths relate to each other. So if you remember, across from the 30, if we call that x, not x is in my distance. If we call this distance x right here, this length. In fact, maybe let's change that a little bit so we don't mix it up with the x that we're trying to figure out the x value of this point. So let's call this length right here A. If that length across from the 30 is A, my hypotenuse is 2A. And the length across from the 60 degrees is A multiplied by the square root of 3. Okay. So if I break down my triangle just a little bit, I can use that information to help me find these distances. Now, the only thing I know is my hypotenuse. I know my hypotenuse is equal to 1. But because of this special triangle, I know that that's also equal to 2 times A. So if I want to get A by itself, I'm going to divide both sides by 2. So 1/2 is equal to A, which means that this distance right here, up and down, is actually 1/2. And this distance, we already knew that that was 1. So what I found is my y value, my up and down right here. So my y value right here is 1/2. Now I've just got to find my x value, which again is easy to do because my x value is just my y value, this distance, multiplied by root 3. So I just take 1/2 and I multiply that by the square root of 3, and that becomes the square root of 3 over 2. So my x distance is the square root of 3 over 2. Now what's nice about that is from there, I don't have to do any more math. I can find all of these other coordinates by manipulating this one right here. And the reason I can do that is because if I look at this triangle, if I look at this one, I don't know this one yet, but if I do what I did the first time, now this is 30 degrees, and this up here is my 60 degrees. So my 30-degree side, this distance is now my x value. So my y value just became my x value. So up here, this becomes 1/2. And my y value, this distance right here, is the same as my x value that I already found, which was root of 3 over 2. Okay. Now from there, you can do the same thing to find all the rest of these parentheses, these unknown coordinates. For example, this one right here, this angle relates to this angle here, this radian. So if instead of going to the right root 3 over 2, I'm going to go to the left root 3 over 2, but I've got to do a negative because I'm going to the left. But I'm still going up the same distance, which is just 1/2. Okay, so from there, see if you can fill out the rest of this circle. See if you can take the pieces that we know and use those to fill out the rest of these unknown coordinates. And what we'll do in class, we're going to do this a couple of times in the classroom from start to finish. And slowly, hopefully you can start doing this without any guidance. You can just do it on your own. But for now, let's move on to some new stuff this year. The first thing that I want to talk about is, well, just kind of the starting point here is our secant and tangent lines. And it may have been a while since you've seen those two words or used them. And in fact, when you saw them, you probably heard the word secant line when it was being referred to in a circle. And if you remember, a secant crossed the circle in two places. It crossed the circle here and here, and that was called a secant line. Well, a secant line can also cross a graph or a function in two places, and we still call that a secant line. And similarly, a tangent line, when you learned that with circles, was a line that touched the circle in just one place. There was only one point where they touched, and that was called a tangent line. And now we have tangent lines on any curve, not just circles. We can have that on curves of functions. And it does the same thing. At this point on the curve, on the function, my tangent line only touches it in one place. Okay. Now what we're not as interested in the lines themselves as in what we can use that information to find. Okay, so the part that I'm interested in with the secant line, first of all, is I'm interested in the slope. I'm interested in that rate of change. As I go from P to Q, I'm interested in how fast am I changing? What is the slope of that line that goes from P to Q? So I'm interested in, and remember, M represents slope. So I'm interested in the slope of my secant line, which is going to eventually help us find the slope of a tangent line. Because this slope, you found this since what, 7th grade? You've been finding the slope of lines like this. I don't know, do you remember how to do that? You have 2 points, and you take x2 minus x1 on the bottom, and y2 minus y1 on the top. You guys would call that rise over run. How much am I rising? How much am I jumping? So that would help you find your slope. Now, what we're interested in is not just the slope of a secant line. What we're more interested in is finding the slope of a tangent line, which gets a little bit harder because we're missing that second point. This one is really easy to do because I just take the 2 points. I find those values. For example, this one, P, is what? We are at 1, and we're down, it looks like about -2. And our Q is we're going to round that to 3. I might be off just a little bit. And we're up, let's say 12. So if I wanted to know my slope, I would just take my 12 and I would minus -2. And on the bottom, I would take my 3 and I would minus 1. So 10 minus -2, that's 14. And 3 minus 1 is 2. So my slope of that secant line is 7. That was really easy to find. Now with a tangent, I only have 1 point. I don't have that second point to help me find a slope. And that creates a little bit of a problem. And for now, the best thing that we can do is what we're actually going to do is we're going to take these 2 points and we're going to move them closer and closer and closer together. And as we move them closer together, the slope between those 2 points is going to get closer and closer to the slope of my tangent line. As my points get closer and closer together, my slope is going to get closer to what I'm looking for. Okay, so here's kind of a diagram just to show you what we're talking about. So I'm taking this point up here, and I'm slowly moving it closer and closer to my starting point, my 1, 1. So right now, with the point clear up here, this table shows me that my slope is 3. But as I get closer to 1, 1, my slope becomes 2.5. And as I get closer, my slope becomes 2.1. And we're only at this point, we're still pretty far away. I know that seems really close, but when I say we want to get close, I mean we want to get so close that we can barely tell it's not the same point. And right now, there's still a little bit of a distance right there, but we're getting closer to what number? It looks like we're getting closer to 2. So that might be the slope, and we could keep going. I could pick an X even closer and keep going to see what we can find, okay? So let's kind of break this down a little bit. Now this picture, I know it looks like a big mess, but it's something that you're going to need to be able to pull some information from. So we're going to go through, we'll look at the picture and then talk about some of the formulas that we can pull from that. So this purple line right here is labeled f of x. So that means that's my function. That's the curve that we're talking about. And on that curve, I have 2 points. I have P right here, and I have Q. And those are labeled, P is labeled x naught, y naught, and Q is labeled with an x1 and a y1. So that just means each of these has an x and the y that correlates with it, okay? Then if I look at this h equals x1 minus x1. All that's saying is right here, this length on my x is x naught. This distance right here is my x1. Now what h represents is how far in between, how much distance is in between there. That's finding my run. H is just saying how much further do I go when I go from P over here to Q? And that's my H. My Y, we don't have a special name for it. We just call that, right now, that's still just Y1 minus Y naught, because that number depends on my X. So we're going to leave that Y1 minus Y naught. So that's the picture that we're dealing with. And then it just gives you a few formulas. And the biggest reason I want to look at these is I want you to be comfortable with what looks like kind of a mess. So what it's telling me right here is the slope of the secant line is equal to rise over run. That's 7th grade right there. You've known that for a long time. But then it turns it into, it gives rise over run a formula. And you're used to probably y2 minus y1 over x2 minus x1. Same thing, y1 minus y naught divided by x1 over x naught. And what this y naught and x naught means is the same thing that the y1 did. That's just another point. We can call those whatever we want, as long as you know that this x and y go together and this x and y go together, okay? Up to this point, you've used coordinate pairs quite a bit. You've used order pairs like this. You've had x1 and y1 written out for you like this. This second formula right here, I just want you to recognize that it's the same thing, but it's in what we call function notation. Instead of x and y, you notice that my x's are still on the bottom. I still have x1 and x1. But function notation, if I have an x and I plug it into a function f of x, remember, here's my x value. When I plug it in, I get a y value. So it's just replaced the y's with function notation. So this f of x sub 1 just means y sub 1. And this f of x sub naught just means y naught. Okay, so it's the same formula. It's just in function notation. Okay, here's my x. Here's what happens when I put x into the function and get a y value. Okay. Now, what we're trying to do, we're not going to worry about these bottom ones too much right now, but what we're trying to do is we're trying to take this q value, remember, and we're trying to move it closer and closer and closer to this p value. So basically, I'm taking this x and I'm moving it closer and closer and closer to my original x value. So x is trying, that distance between x, that distance right here, we're trying to make that really small so that we can get really close to our tangent slope. Okay, and that's what it means right here when it says limit. It's saying that is h, as that distance gets really close to 0, then my slope gets close to my tangent slope. All right, so let's put some of this into, let's actually do some math here. These are the formulas that I want you to, kind of the ones that you need to know. The first one up here at the top, this one's a big one. It's something that if you don't have it memorized already, you've got to figure it out. This one, it's saying the same thing twice. The slope is the rise over run, or the y2 minus y1, x2 minus x1, and it's just writing it in two different ways. Be comfortable with both of those forms. The slope of the tangent line, we're going to ignore this one for just a minute. The slope of the tangent line, when I move really, really, really close to my original x, when I make this h get really close to 0, when my x's are really close to each other, arbitrarily close, meaning they're pretty much the same point, then that gets me closer to the slope of my tangent, okay? And then at the end of the day, we'll have one problem that you need to use your point slope form from algebra. And just remember, you take your y minus your y naught, and that equals your slope multiplied by the x minus the x naught. So we're going to use those. Make sure you have them written down somewhere. Okay, so here's our first example. If you're given this function, f of x equals x squared minus 3x minus 4, it wants us to find the slope of the secant line between 2 points. It wants me to find the slope of the tangent line at a specific point. And then it wants me to find the equation of the tangent line at that point. For your first problem, that's a lot to do at once. Good news is most of it you've already done already. Okay, so slope of the secant line. So I'm looking for the slope of my secant, which, remember, that's just your y2 minus y1 over x2 minus x1. It's as simple as that. So it gives me an x value, 2 x values that I need to use. So let's go ahead, and I don't know what the y values are at those points. There's a couple of ways I can find that. I can look at my graph. My blue line represents the function. So when x is -3, so when x is -1, -2, -3, my y value is right about here, which looks like 14. So when x is -3, then y is equal to 14. At least that's what it looks like. When x is 2, so when x is 2, my y value is down here at -6. So when x is equal to 2, y is equal to -6. Now, if it didn't give you the picture, this one was nice because it gave me the graph. It did a lot of the work for us. If it had not given you the graph, do you remember how to do that? You would take your x values and plug them in to find your y values. So f of, let's plug in -3. So f of -3 squared minus 3 times a -3. I better put that in parentheses or I'm going to make a mistake. Minus 4. So that becomes 9. -3 times -3 is another 9. Minus 4 becomes 18 minus 4 is 14, which is what I thought. So lots of different ways you can find that. If you really wanted to, you could even plug this into your calculator, this function, and use the table to find your answer. So let's do that one. Let's take my y equals, and we're going to plug in x squared minus 3x minus 4. And I could graph that, and it's going to give me the picture. But I'm not really interested in the whole graph. All I'm interested in is those points. So I'm going to go to my table. I'm going to go to second table. And I'm interested in when x was equal to, let's get this window to go away. Nope, not you. I want you to go away, window. I'm interested in, oh, for heck's sakes, when x is equal to -3. So if I type in -3 and hit enter, it tells me that my x is 14. And if I plug in 2, it tells me that my x is -6. I don't care how you find it, but you do need to be able to find it with a picture, without a picture, and without a calculator, because you may not have it on the test. So I've got my 2 points. So let's just plug those in. The slope of my secant line is equal to, let's call this one x1 and y1, and this one x2 and this one y2. It really doesn't matter, but let's do -6 minus y1, 14, over x2, which was 2, minus -3. So -6 minus 14 is -20. 2 minus -3 is 5, which simplifies to -4. So this red line right here, my slope between those 2 points, my secant slope is -4. So that's part A. Now part B wants me to find the slope of the tangent line when x is equal to 1. So when x is equal to 1, it wants to know what is the slope of my tangent line. Now remember, to find that, I need another point. So let's use x equals 1. That's kind of my starting point. And when x is equal to 1, what's our y value? 1 squared is 1, minus 3 is negative 2, minus 4 is negative 6. So when x is 1, y is negative 6. And that looks good to me. But I need a second point. Not just any second point. I can't just pick something over here or over here. I want to pick something so close that it's almost the same point. And I'm going to be dramatic about it because I want an accurate answer. So my second x, I want it to be 1.0001. I think that's dramatic enough. That's really, really, really close to x1, but it's not quite x1. So now I need to figure out what is my y sub 1. And again, I'm going to actually use my calculator because I don't want to plug 1.00001 into x squared and minus 3x. So I'm just going to use my calculator, and I'm going to say if my x is 1.0001, what's my y value? And it tells me that my y value is negative 6. It might be doing some rounding there for me. Let's go just a little bit further away. How about 1.001? Did I do too many zeros again? How about that? There we go. Negative 6.001. So negative 6.001. Okay, so I'm really close on both points. So let's plug them in. Our formula, if you don't remember what it was, we just take that really, really small value and we're going to find the slope. So the slope of my tangent is my y values, so negative 6, and I'm going to minus negative 6.001. That's going to go on top. And on bottom, I moved 0.001, right? Because my x value, we didn't use this one. We used 1.001. So negative 6 minus 6.001 is actually 0.001 over 0.001, which is just 1. Except for, where are we? Do we have our negatives right? No, we're at a negative. Because our slope is going down. So we've got a sign somewhere wrong, right? What did we do? We did negative 6 minus our negative. And then we did, oh, that's what we did. There's my negative sign. See, that's not looking right because I know my slope should be going the other direction. I found the distance between these two, but I should have put 1 first and then subtracted 1.001, which would have given me negative 0.001. So my distance, my slope, excuse me, is negative 1. So be really careful with your signs. I was skipping ahead and I probably should have taken my time a little bit more right there. So this was my y2 minus y1 over x2 minus x1. All right. So my slope is negative 1 on that tangent line. When I get really, 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 really close to my tangent, my slope becomes negative 1. Okay, let's do another example. We're not ready to do another example. I thought I was missing something. Part C, the equation of the tangent line. So part C, it wants our equation, which remember is y minus y1 equals the slope of my tangent line times x minus x1. So as we're pulling that from here, that's where we got it from, just our formula back there. So my y is just y. My point that I'm using is what was our point? X was equal to 1. And when X was equal to 1, Y was equal to -6. So my Y is minus a -6, and that's equal to my slope, which was -1, multiplied by X minus 1. So this simplifies to Y plus 6, and this simplifies to -X plus 1. Now, a couple of things that I really want you to understand on the AP Calculus test. You don't have to simplify. If you had written this as your answer, if that's correct, you would have gotten the answer correct. So if it's not an easy simplification, don't simplify. You might make a mistake. This one was pretty easy to simplify, so we went ahead and did it. But on the AP test, remember, you don't have to simplify at the end unless it specifically tells you that you need to. Okay? Now, we can also check our answer on the calculator. If I go back to, this is kind of a cool feature that these calculators have. I've got my function in here still. This time, what I want to do is I can actually make it draw my tangent line. So if I do secant program, there's this draw word right here. So secant program is going to take me to the draw menu, and I want it to draw a tangent line. So I go down to 5, draw me a tangent line when X is equal to 1. And I'm getting an error. Why am I getting an error? Go back to my graph. Let's go to standard window, zoom, standard. Maybe because I drew it without being on my graph. So from my graph, if I go secant program, tangent, which is number 5, there we go. It asks me for my X. So when my X is equal to 1, and look, it draws me a tangent line, and it tells me that the function is Y equals -1x plus a -5, which looks really close to what we had. The only difference is they simplified one more step. They -6 from both sides. So Y equals -x. 1 minus 6 is -5, which is exactly what they had. And look at their slope right in front of the X. The -1 is the same as what